All right, let's take some notes on thermal energy. First thing I want to do is define what is energy. So we talked about this during your warm-up yesterday. What is energy? So energy is the ability to cause change. So that is the definition of energy. It's the ability to cause change in something. So that can be in different forms. It could be electrical energy. It could be kinetic energy, potential energy. It could be light energy, sound energy. Anything that can cause change could be considered energy. Potential energy is stored energy. So it is stored up. So it has the potential to cause change. Whereas kinetic energy is the energy of movement, which we also talked about yesterday. So that prefix in kinetic, K-I-N, refers to movement and motion. So it's the energy of movement. Now, energy is a property. It's not a thing. It's not an object. It just is the ability to cause some sort of change. Right? So on your note sheet, you'll see that you have blanks after each one of these vocabulary terms. So please copy down those definitions. You can pause if you need to. All right, the kinetic energy of molecules. All matter is made up of atoms and molecules that are constantly moving. They have kinetic energy. We cannot see the atoms and molecules moving because they are too tiny. So like we mentioned, everything, so if we said all matter has kinetic energy, that means everything is moving. The pencil in your hand right now, yes, you're moving it, but even when that pencil is still in your hand, those little atoms in your pencil are moving. And you're actually transferring more heat, more thermal energy from your hand into the pencil. So in the parts of your pencil that you're touching, those particles are actually moving even faster than the parts of the pencil that you are not touching. So everything, okay, has kinetic energy. It has some sort of motion. All right, so in the box on your notes, it says molecules in motion. You're just going to draw, not as many as here, but just draw a couple little circles representing molecules, a couple of circles with some arrows showing that it's moving. Okay. Thermal energy is the kinetic energy of moving particles. So now we're going to talk about thermal energy. So it's the kinetic energy of moving particles. So it's that movement of particles. Thermal energy is sometimes called heat energy. So often when you hear the word thermal, it refers to heat. Okay, so what is temperature? So we defined this yesterday, but we'll define it again. So temperature is a measurement of the average kinetic energy of the particles in an object. So temperature is a measurement of the average kinetic energy of particles in an object. So we're measuring how fast those particles are moving. Particles that move slower have a lower temperature, and particles that move faster have a higher temperature. Okay, so I don't know if this animation's not working in this slideshow, but in this picture, in this box right here, these molecules should be moving a lot faster, and in the cold water, the molecules are moving a lot slower because they have less kinetic energy. So in your first box that says hot water, you're going to draw, actually let me see if I can flip to my DocuCam real quick. That'll make it easier. All right, here we go. So here's your notes right now. Okay, so in the box that says hot water, okay, you're going to draw some molecules with, I call these little wings. So if they're going faster, they're going to have more wings. So these molecules are going to have 3 wings showing that they're going really fast. Okay? And I'm going to put a little note that this is higher kinetic energy, high KE. And then in the cold water, they're not moving as fast, so I'm just going to do one little wing. Okay, and this has low kinetic energy. Okay? All right, so back to the slideshow. Okay, energy can be transferred into an object, thereby raising its temperature. So we can transfer energy into an object. And when we transfer that energy, it can raise temperature. Okay, so like you're holding your pencil right now, you're transferring energy from your hand into your pencil, raising the temperature of that pencil. All right, in your Watch Pot Never Boils at-home experiment that you completed, you were transferring energy from your stove into that pot of water, thereby raising its temperature. All right, the temperature brain pop we watched for a warm-up today, so we'll skip that. So let's talk about measuring temperature. So scientists measure temperature with a thermometer. Write that down. Since each particle in motion has different speeds, you are actually measuring the average kinetic energy of all the particles in a substance or object. Okay, so what that's saying is in, let's say, a pot of water, some of those molecules are going to be moving faster than others. So what we're actually measuring is the average of all of those particles, how fast they're moving. There are 3 common temperature scales for measuring temperature. There's Fahrenheit, Celsius, and Kelvin. So we'll go over each one of these in the following slides, and you'll record the information in that table on the back of your notes. So we're going to compare these 3 scales. Fahrenheit, so go ahead and write down Fahrenheit, is the scale most commonly used in the United States. Okay, so if you're watching the weather in the morning and they talk about what temperature it's going to be outside, they're usually giving the temperature in Fahrenheit. The boiling temperature of water in Fahrenheit is 212 degrees Fahrenheit, and then the freezing temperature is 32 degrees Fahrenheit. So that's just some common information you should know when water freezes at 32 degrees Fahrenheit. Okay, now Celsius is a scale most commonly used in the rest of the world and by scientists. Celsius actually makes a lot more sense, and you'll see right now. So the boiling temperature of water is 100 degrees Celsius, and the freezing temperature of water is 0 degrees Celsius. Okay, so basically this scale is based upon the boiling and freezing point of water. If you've ever been anywhere else in the world and they talk about the weather or temperature, they're always using Celsius. It actually makes a lot more sense than our scale that we use, which is Fahrenheit. Scientists will also always use Celsius. Okay, the Kelvin scale is not used very often. The Kelvin scale is special though because 0 Kelvin is when all molecular motion stops. And this is also known as absolute zero. So this means that something has basically no temperature. There's no movement. There's no thermal energy there. So this doesn't exist in nature on Earth. They've tried to synthesize this in a laboratory to get this to happen. But 0 Kelvin would be when all molecular motion stops. So the boiling temperature of water in Kelvin would be 373 Kelvin, and the freezing temperature would be 273 Kelvin. Okay, so notice for this one we actually don't use a degrees with this unit. All right, So moving on to some heat concepts. So thermal expansion. Thermal expansion is an increase in the volume of a substance when the temperature increases. Okay, so volume is how much space something takes up. So most materials are going to expand when they're heated, so they're going to get bigger. The reason why they expand is because there are active particles that are going to move away from each other. So those particles, when they start moving really fast, they start heating up, they're going to start bouncing into each other. And as they're bouncing into each other, they're creating space. And that space is that thermal expansion that we see. So this happens everywhere. Okay, when things get heated, they're going to expand. If you've ever roasted a marshmallow, you might notice that that marshmallow, when it's in the heat, starts to kind of inflate and get larger. If you got any of those marshmallow peeps for Easter, those little peeps, a fun little at-home experiment you can do. You can take one of those and stick it in the microwave and heat it up, and it'll actually it'll expand. It'll grow into a big chicken. This picture here in this slide is showing what we call, it's called a thermal expansion grate. So you have seen these before, but may have not realized it. On the Coronado Bridge, there are these thermal expansion grates that you see right here on the top. So this is an engineering solution to the problem of the concrete bridge during the day is going to expand, and then at night when it cools down, it's going to shrink. And that constant expanding and shrinking and expanding and shrinking could affect the integrity and the structure of that bridge. So engineers design these thermal expansion grates that when it heats up and expands, those little teeth come together to give it that extra kind of buffer to expand, and that when it cools off at night, then they're going to separate back out. So it just helps preserve that structure of the bridge. So look for those next time you're driving across the bridge. All right, another concept with heat, thermal energy and mass. An object's mass affects its level of thermal energy. The higher the mass, the higher the kinetic energy. Okay, so you haven't seen the Bill Nye yet, but in Bill Nye they talk about which has more kinetic energy, an ice sculpture or a lit match. So you might think, well, the lit match is hotter, but since the ice sculpture has more mass, it's actually going to have more thermal energy, because thermal energy is just the kinetic energy of those molecules. So in the picture below, okay, which has more thermal energy, hot cocoa or a bathtub of lukewarm water? Okay, so the answer would be the bathtub because it has more mass. All right, specific heat is another thermal energy concept. Specific heat is a measure of how much energy it takes to raise the temperature of a substance. Specific heat is a property that is specific to a given type of matter. Okay, so it's saying this specific heat is how much energy it's actually going to take to change temperature. Metals have a low specific heat. You don't need to write this down, so they heat up quickly, and water has a high specific heat, so it heats slowly. So this tells us that different types of matter can absorb more or less energy before temperature is going to change. So this explains why sand at the beach gets hot a lot faster than the water. Or if you're at a pool, the wet concrete feels cooler than the dry concrete because they have different specific heat. All right, heat is the transfer of thermal energy from an object of higher temperature to an object of lower temperature. So in the boxes below where it says a box arrow to another box, you're going to write high to low. Okay, so we're going from high temperature to low temperature. That is the direction that heat travels. Thermal energy will continue to move from warmer to cooler objects until the temperature is the same. So until the average kinetic energy is the same. So when it reaches equilibrium, then that thermal energy will stop moving. Okay, we made it through the notes. So hopefully some of those concepts make sense. We will continue covering them, though, over the next couple weeks. All right, thanks.